Hello, my name is John Moyer, and I want to welcome you to the NIH Office of Disease Prevention's Methods Mind the Gap webinar series. This series explores research design, measurement, intervention, data analysis, and other methods of interest to prevention science. Our goal is to engage the prevention research community in thought-provoking discussions, to promote the use of the best available methods, and to support the development of better methods. Before we begin, I have some housekeeping items. You can submit questions during the webinar via the chat pod. You'll need to open the pod by hovering your cursor at the bottom of the Zoom window and then clicking on the chat icon. Please direct your questions to hosts and panelists. We will open the floor to questions that have been submitted via the Zoom chat pod at the conclusion of today's talk. The slides and video recording will be posted on our website, prevention.nih.gov/mindthegap, in approximately 2 weeks. Lastly, we would appreciate your feedback about today's webinar. Upon closing, you'll be asked to complete an evaluation. We would appreciate your feedback as it will help us improve this webinar series. At this time, I'd like to introduce Dr. David M. Murray, Associate Director for Prevention and Director of the Office of Disease Prevention.
Thank you, Dr. Moyer. Today's speaker is Dr. Matthias Cattaneo. Dr. Cattaneo is Professor of Operations Research and Financial Engineering at Princeton University. His research spans econometrics, statistics, data science, and decision science, with applications to program evaluation and causal inference. Most of his work is interdisciplinary and motivated by quantitative problems in the social, behavioral, and biomedical sciences. As part of his research agenda, he's developed novel non-parametric, semi-parametric, high-dimensional, and machine learning estimation and inference procedures with demonstrably superior robustness to tuning parameter and other implementation choices. Dr. Cattaneo is an elected fellow of the American Statistical Association, the Institute of Mathematical Statistics, and the International Association of Applied Econometrics. He serves on the editorial boards of numerous journals, including the Journal of the American Statistical Association and Econometrica. In addition, he is an Amazon scholar and has advised several government, multilateral, nonprofit, and for-profit organizations around the world. It's my pleasure to welcome Dr. Matthias Cattaneo.
Thank you. Thank you so much for having me, and welcome everybody. So today I'll spend about 40 minutes giving an overview of recent methods on regression discontinuity designs. If you're interested in learning more about the background material, there are tons of references provided through the webinar website, and also available in my own website listed here. So the way I organized this presentation is essentially in 4 or 5 parts, really. I'll devote a disproportionate amount of time to each of them. First, I'll do a quick overview of the different designs, the most common designs that you can find in practice. And then I'll jump in quickly to talk about how to present visually regression discontinuity designs. And then I'll spend the bulk of the time serving rather quickly the 2 main frameworks for the analysis and interpretation of regression discontinuity designs. The first one is based on continuity or extrapolation methods, and these are often the default for most applications. But then also many researchers and scholars choose to employ local randomization methods, which are of course connected but different in terms of their underlying assumptions and consequently the interpretation of the results. If time permits, I'll also talk a little bit about modern falsification and validation methods, but perhaps I'll run out of time, in which case the slides will provide a little bit of a hint, and again, the references will give you more. So let me get started with some basic introductions. So regression discontinuity designs are a methodology that belongs to the class of observational methods. That is, they try to estimate treatment effects, causal treatment effects under some assumptions, given observational data. So other members of this toolkit include well-known methods based on selection of observables, instrumental variables, difference in differences, synthetic controls, and many more. One key advantage of regression discontinuity designs, I think, is that they are simple to explain. And in many ways, one could argue that they are the closest in resembling what an experiment would be. Each of these methods within observational studies try to resemble experimental settings by means of different assumptions. In the case of regression discontinuity design, the core assumption will be a particular assignment mechanism of the treatment itself. In particular, it will rely on an objective basis for assignment. So I'll discuss more in a minute. The beauty of this particular assignment mechanism is that it generates many important testable implications that one can use to validate and falsify the design in itself. And so in that sense, it's also quite powerful. I should mention, it's very important, I think, that one key limitation of traditional regression discontinuity designs is that they will identify and ultimately say something about a very particular parameter of interest. And this parameter might or might not be what the researcher cares about. It is certainly different in general than the type of parameters that experiments would identify and many other methods, even observational methods. Okay, what is the core of any regression discontinuity design? Well, you need to have a triple. You need to have three things, and this is the only way that a regression discontinuity design comes to life. You need to have a score. This is a variable that is assigned to every unit in the analysis. And then you need to have a cutoff that determines whether or not units are assigned to treatment. So in this simple plot, all the units with a score greater than C are assigned to treatment. All the units with a score below C are assigned to control. And so the name, regression discontinuity design, comes from the fact that there is a sharp discontinuity. The probability of treatment assignment jumps discontinuously from 0 to 1 at the cutoff point. This is a quite common design in biomedical sciences, as well as in many other sciences. Whenever there is some sort of scoring assigned to patients, and decisions are based on certain scores exceeding particularly set cutoff, then that generates a regression discontinuity design. Intuitively, some patients would receive a score that is near the cutoff, but to the right. Some patients will receive a score that is near to the cutoff, but to the left. To the extent that these patients are similar in all observable and unobservable characteristics, other than having a score slightly different because it's either above or below the cutoff, then they will be exposed to dramatically different treatment arms. So the core idea underlying all regression discontinuity designs is one of localization. Ultimately, you need to look at units that are near, in terms of their score, near to the cutoff determining treatment assignment. And this is the sense in which the parameters that ultimately we learn about, the treatment effects, the causal treatment effects that we learn about, are necessarily different. We can really only learn about the treatment for those units whose scores are near the cutoff. We cannot really say much about units that are away in terms of their score values, away from the cutoff. There will be methods, there are methods for extrapolation within the RD literature, but we will not discuss them today. So there are many variants of regression discontinuity designs. In terms of identifying treatment effects, you need to sort of settle with some assumptions, like any other observational method. So in the context of RD, the two more popular ones are the continuity or extrapolation framework and the local randomization framework. And they are complementary to each other. They have different assumptions, and they often lead to interesting, potentially different conclusions, although ideally you would expect the two to complement each other. And so the effects should be compatible whenever you use one set of assumptions or the other. But ultimately, it is at the discretion of the researcher and, of course, the understanding of the specific application, which of these frameworks is the best. Another big difference across regression discontinuity signs is the nature of the scoring variable. In many applications, the score is continuous, but in some cases, the score might have a repeated value. Sometimes the score is age. For example, you might be eligible for Medicare only when you turn 65. So if you have 64 years of age, or if you have 65 years of age, well, you're right at the cutoff, but the score variable, the variable determining treatment assignment, is discontinuous. It goes in integer values 1 year at a time. So that would be an example of a discrete score in the regression discontinuity design, and one that will have very few unique values, right? So there will be a lot of repeats. Many people will be 64 years old, many people will be 65-year-old, but ultimately there will be tons of repeats, but very few unique values on the score space. So there will be little variation, relatively little variation in the score domain. Okay, great. So in terms of settings or different regression discontinuity designs, well, here the list goes on, and every month a new flavor of regression discontinuity designs comes about. So today I'm going to briefly talk about the two most popular ones, which are the traditional cross-sectional, sharp, and fuzzy RD design. I'll touch base briefly just for illustrational purposes, the multi-cutoff and the multi-score or geographic RD design. These are very popular methodologies exploiting the core idea of RD. Again, the core idea of RD is the existence of a sharp discontinuity in treatment assignment based on an observed scoring variable. Why? Because then we can zoom in to the regions where the discontinuity happens, and then compare those units that are barely below or barely above, barely to the left or barely to the right of that point of discontinuity. The hope being that those units are essentially assigned at random, right? So ultimately, the regression discontinuity design tries to resemble a local randomized experiment. And I'll talk more about this, of course, in the next few slides. In terms of parameters of interest, there is also tons of alternatives depending on the problem. Here, I'm going to focus exclusively on average treatment effects. Very standard, very simple, just to get ideas off the ground. I should mention that there are important parameters that are related to this problem of extrapolation, trying to learn what the effect of the treatment would be for those units that are not near the cutoff. Maybe they are far away to the left, far away to the right. Maybe they are far away from the boundary in a geographic application, perhaps to one side or the other. And so those are very interesting parameters, but they will be beyond the scope of today's talk. Okay, so what is the basic setup for any regression discontinuity design? Well, it's no different than that from a randomized control trial, an experiment. And so this slide here seeks to compare the two. So in a typical randomized control trial with two treatment arms, control and treatment, say, you will have two potential outcomes. Those are the outcomes that would have happened under each of the treatment assignment arms. And you will have a bunch of units. These units will be indexed by I from 1 up to n. So you have n units. At the core of a traditional randomized experiment, the treatment assignment, the variable telling us whether a unit was assigned to treatment or to control, is independent of everything else. In the simplest possible case, it's just a randomized assignment that had nothing to do, certainly not with the potential outcomes or the potential gains of the units in the analysis or many other characteristics, pre, post, whatever. So this variable is independent of everything else. And ultimately, the fundamental problem of causal inference is about learning something interesting about differences of features of the potential outcomes for control units and treatment units. The most common one is the so-called average treatment effect, which essentially compares the average response had all units been assigned to treatment vis-a-vis the average response had all units been assigned to control, right? And ultimately, we are able to identify this important parameter of interest, this causal parameter, by virtue of randomization. We can, because assignment to treatment and control is at random, we can effectively compare the average, the observed average response of the treated units against the observed average response of the control units. And that will give us, under appropriate regularity conditions, an unbiased, potentially consistent estimator of the average treatment effect. So what does it change in regression discontinuity designs? Well, this is what it changed. So basically, you have a few adaptations, a few changes that are key to the way that we think about the problem, right? So here is the first change. There is a particular variable X that plays a crucial role. The role that it plays is to assign units to treatment and control according to a fixed hard thresholding rule. So all the units whose score exceeds the cutoff C are assigned to treatment. All the units whose scores do not exceed the cutoff are assigned to control. So in many ways, it's the opposite of a randomized experiment, right? Here, the random variable treatment is independent of X. Here, in regression discontinuity designs, is completely dependent, is deterministically dependent, in the sharp RD at least. Okay, perfect. So the rest is pretty much the same with one big change. So I want to focus here for a minute because the parameter changes. So in randomized experiments, we look at the average treatment effect in the population. Here, however, we cannot look at that. So instead, what the regression discontinuity design says is intuitively, for the population or the sample, if you like, as a whole, there is no randomized assignment of the treatment. But if I zoom in enough to the cutoff, according to the scoring variable, then as I get closer and closer and closer to the cutoff, units under appropriate regularity conditions become more and more and more comparable in all respects, except that those above the cutoff are treated or assigned to treatment, and all below the cutoff are assigned to control. So we can exploit that, and we can learn something that is potentially of interest. So the parameter changes, and now the parameter is really an average treatment effect, but only for those units whose scores are exactly at the cutoff or near the cutoff. Okay, great. So here's a graphical representation of this idea, right? So for units with scores exceeding the cutoff, let's say this is a conditional cash transfer program. It seeks to improve child health by means of incentivizing households to bring their children to the doctors. And so only households who are eligible would be potentially receiving the conditional cash transfer program, or at least they will be eligible to it. And that will imply that these households have to have a very high poverty index, right? So it's quite common in many of these large-scale conditional cash transfer programs that households are first scored according to a poverty index. And only those households that are sufficiently poor are really eligible for receiving the transfer. Households that are not poor enough, they are richer, are not eligible. So if you think of the score as a poverty index, on the right, you have the poorer households. Here will be the poorest of all, and they become richer, richer, and richer. And at some point, they are rich enough that they become ineligible for receiving the transfer. So naturally, all these households are ordered. And importantly, households here and households here could be quite different. On the right, they're very, very poor. On the left, they are very, very rich. There is no reason why we could compare them and hope to understand the effect of receiving the conditional cash transfer program or any other treatment like that. However, as we move closer and closer to the cutoff, the situation changes. Households that are barely above the cutoff and households that are barely below the cutoff, they effectively have the same poverty index. They are just unlucky. Some households landed on the right, some households landed on the left. So what is the core operative assumption in the background? Well, it's one of continuity. It's one that says, well, in the absence of the treatment assignment, nothing would have changed too much if I moved households a little bit to the right or a little bit back to the left. In other words, if they have gotten a little bit less of the poverty index as assigned to them, or a little bit more when they fill out at baseline time their questionnaire that generated the poverty index, they just got a little bit lucky, a little bit unlucky. They landed on the right, they landed on the left. So ultimately, the idea is there is sort of a local randomization going on. Of course, an easy way and one that we should always be worried about is every regression discontinuity design could be broken if the units themselves are able to systematically place themselves on either side as they so see best. If they could manipulate their own scores, if they could go back to the government and change their scoring and become poorer or richer according to the poverty index, then all of a sudden selection kicks in. Units to the right would be systematically one form or one way, or they will have certain unobserved confounders, and then units to the left will be systematically different. RD designs come to help to the extent that these units cannot have this sort of perfect manipulation of their scores. Okay, so having that in place, then the estimation, at least intuitively, makes sense. You would like to estimate what is the average response of units who are barely to the right of the cutoff, and then estimate what is the average response of the units that are barely to the left of the cutoff. And again, the operative idea is one of localization. So RD designs should always be analyzed in terms of localization. Global fitting, global parametric models is not really a great idea. They bring a lot of structure and parametric assumptions that are not really needed. We would like to localize. The continuity and extrapolation framework is one that goes all the way. Basically, what they do in that framework is they identify the parameter at the cutoff by essentially taking the limit from the left and from the right and pushing to the extreme. So the idea being that we really just only extrapolate all the way to the cutoff. We basically just take the limit, and this continuity kicks in and give us an identification of the treatment effect. A different idea is the local randomization idea. So this one, what it says is, okay, hold on a minute. Instead of taking the limits all the way to the cutoff, why don't we just settle for a region or a neighborhood or a window around the cutoff? And then we think or view the regression discontinuity design as just a randomized experiment within that window. So to be very precise, all the units whose scores land inside the window here would be analyzed as if they had been exposed to an experiment. And the experiment here being, well, either you are treated, then you are on this side, or you are controlled, and you are on this side. So in this framework, which really resembles a randomized experiment locally, only for those units near the cutoff, is ultimately a framework where we can adapt most of the ideas from analysis of experiments. regardless of framework, we need to understand how to localize. And that's very, very important. And depending on the framework, it will change the way we do that. And also in local randomization, we are effectively going to impose stronger assumptions because randomization is a much stronger assumption than just continuity of average effects given score values. So we're going to be modeling more of the underlying data generating process in a local randomization framework than we would in a continuity-based framework. And this is kind of part of the tension between the two. So we'll discuss a little bit of both, time permitting today. So in terms of assignment rules, as I said, I've been talking all the time about treatment assignment as opposed to treatment status of the units. And the reason for this is because either in the sharp design, everybody complies, or we are interested in some sort of intention to treat effect. But of course, in many applications, we know there is imperfect compliance, and that leads to the idea of fuzzy RD designs. In this type of setting, still the regression discontinuity is traditional. So there is a sharp discontinuity in treatment assignment. But then in treatment status, actually, there is imperfect compliance. So in this example, it's a one-sided imperfect compliance. To the left, they comply. Everybody with a score below the cutoff, they remain in the control status through the analysis. But then on the right, units do not perfectly comply. They should have all been treated, i.e. taken on treatment. However, some of them didn't. And so we can compute that. We can actually look at the data and learn what fraction of the units, given the values of the score, of course, what fractions of the units comply with their treatment assignment. So this is a one-sided compliance example that leads to the so-called fuzzy RD design. So today I won't talk about this more than this, but there are tons of different sources that you can consult in the references provided. Okay, great. So I'm going to skip this one in the interest of time. And then let me just quickly mention that there are many other interesting designs. And here I just give two quick examples that I personally like a lot. They bring their own complications, but often they bring great opportunities as well. So on the left, what you have is an example of two cutoff or multi-cutoff RD designs. So this is an example where there is perhaps a population that is exposed to a low cutoff, and there is a population that is exposed to a high cutoff. This is actually quite common. Conditional cash transfer programs, for example, are assigned regionally, and different regions have different cutoffs, perhaps because they have poorer people or richer people, and therefore they can serve more of them or less of them. So they move the eligibility criteria. So in the same country, different regions might have different cutoff points. And so this opens already a very interesting observation, which is we can estimate treatment effects in the low cutoff, we can estimate treatment effects in the high cutoff, but also we could in principle ask questions about extrapolation. So this type of design opens the door for one way of extrapolating treatment effects away from the cutoffs, in particular the low cutoff for the population blue and red, and the high cutoff for the population green and gray, I guess. Okay, excellent. The other design I want to mention quickly is very popular, is a design when you have two scores. And this can happen in education because maybe a fellowship is assigned according to a rule that says that you need to score at least this much in math test and at least this much in language examination. And so it really defines a region of treatment assignment, right? Because there are two scores. Or maybe it's a geographic RD, where again, the idea is that this is a boundary in geography, right? And this might be determined by some institutional boundaries, perhaps state-wise or county-wise or whatnot. And then units that land on one side or the other effectively have different exposures to treatment and control. So again, you could think of RDs happening at each point on the boundary. So you don't have one RD design, you have many. You can compare units from here to here, units from here to here. You can also compare units here. And each of those will be different treatment effects along the boundary. You can also average them out and get a single treatment effect, an average effect across the boundary. So many, many different things can be done. So today I won't discuss those, but the references provide very interesting things. So let me just quickly summarize this kind of introductory section. RD designs exploit variation near the cutoff. You need to localize. Causal effects are different, so they cannot really directly be compared to randomized experiments, even if you had them, because the populations are different, right? So what in the randomized experiments, you are looking at the average treatment effect. In regression discontinuity designs, you are looking only at the units near the cutoff according to their scores. In fact, in regression discontinuity designs, there is no overlap by construction, right? Units are either to the right or to the left. And in fuzzy designs, you might have that. Okay, great. So the next of the points here, I think the most important one is this. As I said before, you need to work near the cutoff. Excellent. So let me mention briefly that over the years, we have developed a variety of packages. And this website here gives you access to all of them. They are available in Python, R, and Stata. And the website also has zillions of different replication codes and data sets that you can play with. So today I'm going to basically discuss perhaps the most popular one, which is called RD Robust, briefly, and that will be about continuity-based methods. So RD Robust is handy whenever you want to estimate treatment effects in RD designs using continuity-based methods. And then I want to discuss a little bit of RD Logrand, which, as the name suggests, focuses on local randomization methods. And so these two are the most important ones, and they combine each other if you want, or complement each other. And then we also have some other ones, including one about power calculations, if you're planning to design some experiments for RD data. And this one here is also quite important. It focuses on a very popular falsification test that is used in regression discontinuity design, which is often called the density continuity test. And so we'll maybe briefly touch on that at the end. Okay, excellent. So let me jump in straight to the core idea of the different estimation and inference methods so we can stay on time. As I mentioned before, we're going to contrast two basic methods. One method will be continuity-based, using extrapolation to the cutoff from nearby regions. The other one will be based on the local randomization, viewing the RD as just an experiment so long as we only look at units that are near the cutoff. So how does the local polynomial or continuity-based method work? Well, here's the basic idea. In this type of setting, we need to choose how we localize, and also we need to choose how we approximate these conditional expectations, these average responses of the different units given their relative scores, their different scores. And so the way that we're going to do this is we're going to use a traditional method in non-parametric analysis, which is known as local polynomial estimation or regression. So in the local polynomial regression, all you have to do is effectively specialize or specify the region where you're going to do the approximation, and then immediately use a low-dimensional polynomial fit to approximate the unknown conditional expectation. So here's the graphical representation of the idea. So you start with the regression functions, which of course you don't know in reality because those are underlying the problem and that you only see data. So we don't really see the functions, we only see the data. Then what the local polynomial method does is essentially to localize. So it chooses a bandwidth h so that only the units that are at most h away from the cutoff are the units used in the analysis. In addition, many times researchers choose a weight. So you can use a uniform weight, or you can maybe do a down-weighting weight. So basically the down-weighting weight will say, give more weight to units close to the cutoff and less weight to units farther away from the cutoff, still within the window. So here is a graphical example of that. Let me show you quickly. These are typical weight schemes that practitioners use often. You can use the uniform weight, you can use the down weight, linear weight, you can use a quadratic weight. Either way is fine. It's just a least squares problem ultimately. So once you have localized to the cutoff. Now you only analyze the units near the cutoff. That's exactly the essence of RD designs. That's what we need to do. So what do you do next? You fit a regression. That's the local polynomial approach. You fit a regression and you estimate what amounts to be the average effect or the average response of the units that are treated, the red units in this case, at the cutoff. And then similarly, you can do it to the left. So after you do it from each side, you can actually take the vertical difference and estimate what the effects are. Okay, and that's exactly what the methodology does. A key point to bring to bear, and this is the core of part of my work in this area, is to note that these fits will carry a bias. That's unavoidable because we are choosing a low-dimensional polynomial approximation for an unknown function that really represents the conditional average effect of the units given the score. And so this bias brings some real problems because we have to be careful about how we conduct inference at the end of the day. And so that is the core of the work that we have done for a while. And so the way I'm going to mention this quickly is by explaining how it's done in practice. So in practice, typically, researchers first choose the bandwidth that determines the neighborhood near the cutoff, and they do it by a very particular rule. They essentially choose the bandwidth that minimizes the mean square error of the treatment effect estimator. And that's a great idea because the resulting treatment effect estimator happens to be a mean square error optimal point estimator. However, because you choose that particular bandwidth, you generate a bias. And this bias generates a distortion in the distributional approximation. And this, believe it or not, is a common mistake that many, many papers have or had for many, many years. They tend to use this bandwidth. They tend to generate their own point estimator, but then they will proceed as if there was no bias. And they will just continue on with the traditional least squares analysis. It turns out that that is wrong. And if you do that, unsurprisingly, the bias will shift you away in the distributional approximation. So here's a little bit of a slide that tries to highlight this idea. So you start with a bandwidth that is mean square error optimal. You grab your treatment effect estimator, you scale it to form your t-test, but then you don't really realize, or for a long time researchers didn't pay attention to this, that indeed there is a first order bias induced by this exact procedure. You cannot just go on and use 1.96 from your Gaussian approximation as the correct quantile. There is a bias that unfortunately shifts the distribution away. And this actually leads to over-rejections of the null hypothesis or confidence intervals that might not cover zero as preset by the theory. And so what we proposed in a sequence of papers is a methodology that essentially generates a bias correction and then on top of it, adjust accordingly the standard errors. And so here's a graphical representation of the idea. So what we call the conventional method, which is this incorrect methodology based on least squares approximations, you will have confidence intervals that as the bandwidth increases, the confidence intervals will stop covering the true parameter of interest quite rapidly. So in fact, you can show that the typical size distortion for a 95% confidence interval would be of the order of 80% coverage. So essentially 15% of the time in repeated sampling, you will not be covering the true parameter, even though you thought you would. And so this, of course, leads to some important implications for empirical work, because you will be over-rejecting the null hypothesis about 50% of the time, incorrectly, of course. So what we propose is this robust method that actually recenters and rescales the confidence interval. So that's very important. We need to recenter them to reduce the bias, but then because we estimate the bias, we also need to expand the confidence intervals. And so this is quite important. And of course, sometimes it leads to confusion because practitioners don't quite know exactly what to report, but it's quite important to understand that these confidence intervals will be centered at a different place, and also they will have a different spread. It will be longer. They will be longer because they account for more variability. They account for the variability induced by the bias correction. Interestingly enough, and unsurprisingly, I suppose, it could go either way, because you could start by not rejecting the null hypothesis, but the recentering could more than compensate for the stretching of the confidence intervals. And then in the application, once you do the robust method, actually you reject the null hypothesis. So it can go either way. Okay, very good. So I have some empirical applications that I could show you, but in the interest of time, I only have 10 minutes. I'm going to skip on the empirical application. If there are questions on the empirics, I would be happy to go over them in the Q&A. And if not, as I said, our website contains tons of practical introductions along with their codes and replication files and data sets. So you can very quickly practice with a few different examples. So let me jump to the other methodology. So as I said, the local polynomial methodology is essentially one where you localize by virtue of choosing a bandwidth, and then you approximate the conditional expectations that you don't know by virtue of a polynomial regression, often a linear regression. Most people would do a linear regression. But then the local randomization methods are a little bit different, right? Because these methods, what they really want to do is effectively, they want to replicate what an experiment would be. And so in an experiment, the core idea is that we would essentially have complete independence of the treatment assignment with the potential outcome. But of course, the treatment assignment in RD is a one-to-one map to the score. So that means that you would have effectively a flat conditional expectation, right? So it cannot be a function of X, because if it was a function of X, then it would be a function of the treatment variable. But if it is a function of the treatment variable, then you violate independence. And so for that reason, you should expect that the conditional expectations are unrelated to the score. That will be the ideal world when you have randomization. But in the regression discontinuity design, of course, that will never happen. So instead, what we postulate, or in this framework, what is postulated, is that there exists a neighborhood determined by, say, W, where inside the neighborhood, it is as if you had a randomized experiment. So in the neighborhood, the assignment, the placement, becomes independent of the potential outcomes. You can be above or below the cutoff, and that leads effectively to a local randomized experiment. And the beauty of this is that once you believe this framework, then you're ready to go, because now you can grab these units, the units that are with a score here, and you can deploy essentially all the ideas and methodology from the analysis of experiments. There are, of course, some caveats, and more importantly, there is an issue of how you determine this neighborhood. In the local polynomial approach, the neighborhood was determined by minimizing mean square error of the point estimator and choosing the bandwidth accordingly. In this framework, the local randomization framework, it is unclear how to actually determine the region where you would be more confident to assume that indeed there is a sort of as if experiment design. And so one methodology that is proposed sometimes for selecting this neighborhood is to conduct a sequence of falsification or validation tests, where effectively you will start with a very large region, and then you will start shrinking the region as you move closer and closer to the cutoff. And at each stage, you will determine a number of units that are candidate, or a window or a region that is candidate for your assumption of local randomization. And in that region, you would grab the information and conduct some sort of test that gives you evidence of indeed having an experimental design, or something that resembles an experimental design. And so an obvious way to do this, and the one that is most popular in practice, is to just say, well, let's conduct a sequence of balance tests. So we can grab some covariates, pre-intervention covariates, or some covariates that we might think are correlated with some other underlying confounders. And then we can start with a large window, and we can ask the question, are the units to the left in that window to the left to the cutoff, and the units to the right of the cutoff, are those on average, they have balanced covariates? If the answer is no, we shrink the window and ask the question again. And then if the answer is no, we shrink the window and ask the question again. And so eventually you will find hopefully a window where their pre-intervention characteristics or their characteristics become balanced. And so this also resembles an idea of a little bit of a matching procedure. So ultimately, by shrinking towards the cutoff, you are finding units that hopefully, if you go close enough, you find units that are effectively, on average, balanced. They have the same characteristics on average on the left in the control group and on the right in the treatment group. And so this is a quite popular methodology. And in reality, what happens to, and this is kind of very interesting from an empirical perspective, I didn't have time to show you data today, but if you play around with the different examples that we have, local polynomial methods tend to select windows that are substantially larger. So they use more observations than local randomization methods. And it's kind of intuitive why, because for the local polynomial methods to work, effectively, all you need is to balance bias and variance in estimating a conditional expectation. And so long as the conditional expectation is not too wiggly or too crazy or doing some weird stuff, typically a parametric polynomial linear or quadratic approximation would be fairly okay. On the other hand, to postulate that the units of analysis are equivalent or as if they had been realized from an experiment, well, that brings a lot of more restrictions. You really are asking for independence on treatment assignment relative to their underlying potential outcomes. And so that is kind of a very strong assumption. And so naturally, it has a better chance of being correct if you are much, much closer to the cutoff. And so it's often the case, of course, it depends on the applications, but you go typically 1 or 2 orders of magnitude. So you can go from using 500 observations with local polynomial methods, continuity-based methods, to maybe 50 or sometimes even 20 observations using local randomization methods. And for that reason, often is the case that in local randomization methods, we use a permutation-based inference that is finite sample valid, because we have so few observations that we use near the cutoff in the context of local randomization that we typically end up using Fisherian type inference, randomization inference in this context, because we want to be cognitive of the fact that we only have a few observations where this assumption of as if randomly assigned would make sense. And so this is, again, another manifestation of the contrast between the two methodologies or the two frameworks. The local polynomial framework does more extrapolation. The local randomization method does more localization, if you like. And so they typically complement each other. And in good applications, you see that both give you fairly consistent and compatible answers, and that's the great case. Of course, there are settings where that doesn't happen, and then you have to start questioning the assumptions and what might not be going the right way in the specific application. Okay, excellent. So with that said, I have about 2 minutes. I'll just briefly put out there one single slide on falsification methods. Let me just say that RD brings to bear an array of falsification methods that exploit the specifics of the design. This is something that is quite cool because I think in many other observational settings, it is the case that you don't really have ways of falsifying the assumptions. I mean, sometimes if you are over-specified, you can falsify an IV assumption. Sometimes we try to falsify selection observables and so on and so forth. We use pre-trend analysis for diff in diff, but usually the toolkit is small. In RD designs, the toolkit is large. We have 5 or 7 different ways of conducting sensitivity analysis and falsification and validation methods, and each of them provide different tests on the design itself. So I don't have the time to really go through them, but let me just say that if you're interested, we have a 2-volume monograph published in Cambridge University Press, and there's a whole section that we devote to these falsification and validation methods that I would recommend you can take a look at. Okay, and so with that said, I think it's 12:49, so I think it's a good time to possibly stop, and I'll turn it back to David. I think he's the host of this, and I'm very happy to take questions or go over anything that might be of interest. And so I was told maybe it's better to put this back on, so I'll do that. Thank you.
Great, thank you, Matthias, very much. Lots of questions coming in. We won't get to all of them, but let's start. We'll start with some simple things. Would a regression discontinuity design ever be preferred over a conventional randomized design if you had the opportunity to use a randomized design?
Oh, that's a great question. So, okay, and now you're putting me on a corner, right? Because I work on RD so much that, I mean, I don't want to put it on second place. But yeah, I would say that unfortunately, or fortunately, if you had the opportunity to conduct a well-designed randomized experiment, then certainly you can always resemble an RD if you wanted to. So by construction, the design of experiment setting will be no worse than a regression discontinuity design. Having said that, it might well be the case that in certain settings, the parameter of interest is the regression discontinuity design parameter. So for example, in auctions, often you care about the marginal winner in a betting situation. And in those cases, that is exactly the RD parameter, right? So you would like to learn something about what would have happened had I bid 1 extra cent or 1 extra dollar, right? And so in that case, the parameter is the parameter of interest. But in other cases, of course, it might not be. In the conditional cash transfer program example, we only learn about the treatment effect for those households that are on the edge of eligibility, right? They barely made it to eligibility, but they could have not. So that means that they are the richest of the eligible ones. But we cannot really say much about what the effect was for the households that were much poorer, nor we could really say much about what the effect would be if we were to roll out the program. Because again, as the households get richer, maybe the effect of the treatment diminishes or increases, who knows, right? So again, RD is local in nature, and that is a limitation.
Thank you. Do we have to have prospective data for a regression discontinuity design, or can we use retrospective or cross-sectional data?
I mean, you don't need to have prospective data, so you can use cross-sectional data for sure. If you had, of course, more data is better, right? So obviously you can design more interesting RDs or even exploit the ideas of RD designs if you had, for example, longitudinal data. Or there is this very interesting design that is called the dynamic RD, where basically they follow, for example, students over time, and the students sometimes score sufficiently high that they become eligible for treatment, but then as the time passes by, they take another exam and now they fall on the other side of the cutoff. Sometimes they fall so out that they're not even in the neighborhood. And so this is very interesting because you have these kind of students falling in and out of the analysis in terms of the RD. And that is also kind of a whole other host of issues that you would need to think about. What it means to be treated, if you've been treated, control, nothing, treated, control, nothing, and whatnot, right? So it's a very interesting design, much more complex than what we discussed today, but it was listed in my slides. So it's kind of useful, it's cool.
Thank you. Based on much of what you said today, the focus in the analysis is on participants whose scores are close to the cutoff, either to the left or the right. And I'm curious, what are the implications for sample size calculations? Are we doing a sample size calculation to figure out how many people we need in the window? Are we doing a sample size calculation to figure out how many people we need, for the whole graph?
That's a fantastic question. So as I mentioned, we have this package that I mentioned before here. Perfect. So among these packages, the one I would recommend and the paper associated with this is this paper here, RD Power. So RD Power is a package that actually allows you to address exactly this problem. So we discussed their minimum detectable effects, as well as power calculations and sample size calculations, both retroactively to analyze data that you already have at your disposal, but also to design new experiments. So in fact, I helped the government of Mexico a few years ago to reevaluate their conditional cash transfer program 20 years later, right? So as you might well know, originally in Mexico, it was called Progresa, and then Oportunidades, and so on and so forth, but Prospera and so forth. But ultimately, they had this very large conditional cash transfer program, and they wanted to know what were the long-term impacts of the program. And of course, there was no randomization. Everybody was served by the program 20 years later, but we can still ask the question, if I were to look at the households that were barely eligible and barely ineligible, how many of those would I have to survey in order to learn something useful about the long-term effects of the program? And at least for those that are right at the edge of eligibility. And so for those things, you can definitely use this type of software and the theory that we develop along the way.
Clearly, the selection of the boundaries for the neighborhood that's very important.
Absolutely.
What sort of sensitivity analysis would you recommend to be sure that the result that we're about to report isn't just strictly a function of those particular neighborhood boundaries?
Absolutely. Fantastic. So let me answer this question. This is key. I didn't have all the time to mention it, but maybe let me jump in actually to the falsification section, even though I didn't have a lot of time. There is this one thing here. Here, look at this. Different bandwidth to test misspecification error and sensitivity. So that's exactly the idea that you were mentioning. So in practice, it's quite often the case that you set on a bandwidth that determines the region around the cutoff, but then you would like to understand if I increase it a little bit or decrease it a little bit, how much the estimates change and whether or not there is enough robustness. And so that idea can be done graphically here. So imagine that you chose the mean square error optimal bandwidth, but now you moved to a bandwidth, let's say H12. So you increase the bandwidth. So that means that you are catching more observations. More observations is great because more observations is less variance, right? So as a general rule, the more data, the less variance. But as you increase the bandwidth, your local approximation could get worse because now you're using a linear model on a region that is larger. And so your linear model might not do as well as you originally was doing. The same way, if you grab your bandwidth and you shrink it, you essentially shrink the neighborhood. Now you are dropping some observations, therefore the variance goes up, but now your approximation can only get better, right? Because your linear model is really approximating the function closer and in a much tighter, smaller neighborhood. And so what I'm trying to say is that there is a trade-off between bias and variance. And so people typically explore this. They have a bandwidth that they consider to be the optimal choice, and then they push it a little bit high, a little bit low, and they try to ask the question, to what extent the results change? And that is a very fine sensitivity approach that we often recommend for a sanity check. You want to be sure that it's not all driven by the particular choice of bandwidth that you decided to use.
Thank you. The scoring variable is likely to be measured with error, which may cause misclassification and possibly misallocation of people to treatment and control. What kinds of challenges or opportunities arise from this in a regression discontinuity design?
That's a great question. And the way that you formulate it is awesome, because this is an example where it's not only challenges, but also opportunities in the following sense. Because you have measurement error, that implies that even manipulation would be harder. right? Because now the variable itself is being shifted by hopefully something that is, I'm talking about classical measurement error. So something that is purely noise. And so that means that units will have an even harder time to place themselves strategically in whatever region above or below the cutoff that they prefer. And so the measurement error is an instance here where a little bit of measurement error could actually be nice for us. It will help us because it will make everything look more like a randomized experiment, at least under reasonable regularity conditions. At the same time, of course, all the usual caveats of measurement error kick in, right? So we have to be cognitive of potential uncertainty quantification issues or attenuation biases and so on and so forth. So ultimately, all the traditional knowledge that we have should play a role. But in this case in particular, there is an opportunity in terms of generating a little bit of randomness that could help us at the end of the day.
I want to thank you very much for your presentation today and for taking these questions. We have a lot more questions, but we don't have more time. So we'll have to pause and I will turn things back over to Dr. Moyer. I will note that we will ask you to provide written responses to some of the questions we didn't get to and post that on the web.
I would be delighted. Yeah.
Thank you.
Thank you, Dr. Murray, and thank you to everyone who participated in today's webinar. On the Mind the Gap website, prevention.nih.gov/mindthegap, you will find several resources for this talk, including the slides and a list of references. We will also be posting a recording of today's webinar on our website in a few weeks. Thank you and have a great rest of your day.